Imagine a question not whispered in a classroom but etched in stardust. A question born from the very fabric of the cosmos. Could a simple element forged in the heart of a dying star, in the crucible of unimaginable heat and pressure, hold a key to one of humanity's most heartbreaking mysteries? A mystery that steals memories, erodes identities, and leaves families grappling with profound loss. Consider lithium. It's the third element on the periodic table, a seemingly unassuming member of the atomic world. A lightweight metal that powers our phones, enabling us to connect, communicate, and navigate the modern world. And stabilizes our moods, offering a sense of equilibrium to those struggling with the tumultuous waves of mental illness. But could this humble mineral, this simple atom, also alter our understanding of Alzheimer's disease? Could it offer a new avenue for treatment, a glimmer of hope in the face of a devastating illness? The universe is full of surprising connections, a web of interconnectedness that spans across vast distances and seemingly disparate phenomena. Cosmic laws shaping both galaxies, the grand spirals of stars and dust that populate the cosmos, and the molecules in our brains, the intricate network of neurons that govern our thoughts, feelings, and memories. When scientists propose using a common mineral, something readily available and seemingly unremarkable, to tackle a complex neurological disease, a condition that defies easy solutions and challenges the very limits of our understanding, they're following a thread that links the ancient with the immediate, bridging the gap between the distant past and the pressing concerns of the present. Imagine a lithium atom, born in a star, forged in the heart of a celestial furnace, now venturing into the human brain to mend what's broken, to restore the delicate balance that has been disrupted by disease. This is not magic, but the application of reason and observation, the scientific method at its finest, a journey from a simple question to a potential breakthrough, a testament to the power of human curiosity and the relentless pursuit of knowledge. Let's follow this journey, tracing the path of scientific inquiry, and see where the evidence leads us, exploring the potential of lithium to unlock new insights into Alzheimer's disease. What is Alzheimer's disease? It's a question that echoes in countless homes and research labs around the globe. At its core, it's a disease of forgetting, a gradual and irreversible decline that robs individuals of their memories, their identities, and ultimately, their independence. Imagine your mind as a grand library, a vast repository of knowledge, experiences, and cherished moments. Alzheimer's is a slow fire consuming its shelves, a silent inferno that gradually destroys the precious volumes within. It starts with recent memories, the events of yesterday, last week, and slowly works backward, reaching further and further into the past, erasing a lifetime of love, laughter, and learning, slowly fading away like old photographs. The physical evidence? What's actually happening inside the brain of someone with Alzheimer's? Plaques, sticky clumps of beta-amyloid protein, accumulate between nerve cells, disrupting communication, and tangles, twisted tau fibers, form inside the neurons themselves, choking them from within, disrupting and destroying brain cells. This dual attack leads to widespread neuronal dysfunction and ultimately, cell death. This process can begin years, even decades before symptoms appear. A silent progression that makes early detection so challenging. As the brain struggles to compensate, rerouting neural pathways and working overtime to maintain cognitive function. Eventually the damage overwhelms, the brain's compensatory mechanisms falter, and the symptoms of Alzheimer's become apparent. Shrinking memory centers like the hippocampus, the brain's crucial region for forming new memories. The tragedy of Alzheimer's is its relentless cascading failure at the cellular level, a devastating chain reaction that spreads throughout the brain. We know about plaques and tangles, these hallmarks of the disease that can be seen under a microscope, but their root causes remain elusive. The precise triggers that initiate this destructive process are still largely unknown. Genetics, environment, lifestyle, all likely play a role in the development of Alzheimer's, or all three, interacting in complex and poorly understood ways. It's a puzzle with many pieces. To intervene, to develop effective treatments and preventative strategies, we must first understand what sparks this fire in the mind's library, what sets this devastating cascade of events into motion. That's the challenge facing neuroscientists worldwide, a global effort to unravel the mysteries of Alzheimer's and bring hope to millions. Treating Alzheimer's, a devastating neurodegenerative disease, is one of medicine's toughest challenges, demanding innovative strategies and relentless dedication from researchers worldwide. This is partly because of the brain's own defenses which, while crucial for normal function, can also hinder therapeutic interventions. The blood-brain barrier is a gatekeeper, a highly selective membrane that protects the brain from harmful substances. Unfortunately, it also ends up blocking most drugs from reaching brain cells, making effective treatment incredibly difficult. By the time symptoms appear, such as memory loss and cognitive decline, much of the brain is already damaged, often irreversibly, with significant neuronal loss and synaptic dysfunction. It's like fighting a fire after the forest is gone, trying to restore what has already been destroyed. Therefore, early intervention is key, aiming to slow down or even prevent the progression of the disease. But detecting the disease before symptoms manifest is a massive challenge, requiring sophisticated diagnostic tools and biomarkers. Alzheimer's is not a single failure, a simple cause and effect relationship, but a symphony of dysfunction, a complex interplay of various pathological processes. This includes protein misfolding, leading to the accumulation of toxic aggregates, inflammation, contributing to neuronal damage and synaptic loss, and vascular and metabolic changes, impairing brain function and accelerating disease progression. Drugs that target one problem such as amyloid plaques often fail to address others, neglecting the multifaceted nature of the disease. This leads to repeated disappointments in clinical trials, highlighting the need for more comprehensive therapeutic strategies. However, each failed trial teaches us more about the disease's complexity, providing valuable insights for future research endeavors. This frustration led scientists to look beyond complex drugs and intricate biological pathways to something simpler and older: lithium, a naturally occurring element with a long history of medical use. Sometimes the best hope lies in the most fundamental elements, in harnessing the power of basic chemistry to address complex biological problems. A new approach, a paradigm shift in how we tackle Alzheimer's, was desperately needed. Why lithium? This simple element has been used for decades as a mood stabilizer. Scientists discovered lithium can influence cellular pathways linked to Alzheimer's, especially the enzyme GSK3-beta, which drives tau tangles. The hypothesis: could microdoses of lithium calm this enzyme and slow the disease? To test it, researchers used genetically engineered mice that developed Alzheimer's-like symptoms. They gave some mice microdoses of lithium, far lower than psychiatric doses, and others a placebo. The goal: see if lithium could protect memory and brain health without side effects. Behavioral tests, like water mazes, measured the mice's cognitive abilities. The stage was set for a powerful experiment. The results were astonishing. Placebo-treated Alzheimer's mice showed severe memory loss, struggling in mazes. But lithium-treated mice navigated mazes almost as well as healthy mice. Their memory loss was prevented, or even reversed. Brain analysis revealed fewer amyloid plaques and tau tangles in lithium-treated mice. Lithium seemed to fight the disease on both major fronts, acting as a master regulator. This wasn't just symptom relief, it disrupted the disease's core pathology. A low-cost, safe element halted Alzheimer's progression in mice. The findings sent ripples of excitement through the scientific community. Of course, this was just one study, in one type of mouse. But it opened a surprisingly simple new avenue for research. But a mouse is not a person. Treatments that work in mice often fail in humans, whose lives and brains are far more complex. The mice in this study were engineered to mimic some aspects of Alzheimer's, but not its full complexity. Human Alzheimer's develops over decades, influenced by countless factors. A treatment must be safe for long-term use, something only human trials can confirm. The lithium microdoses seem safe in mice, but we need years of data in people. The mouse miracle is a clue, not a cure. A promising lead for further research. It points us toward the lithium pathway as a new direction. But the journey from lab bench to bedside is long and uncertain. Only more science can bridge the great divide. What's next? Replication. Other labs must confirm these results. If the effect holds, research moves to human trials, starting with safety studies in healthy volunteers. If safe, trials in early Alzheimer's patients will test for real-world benefits. The final hurdle: large, double-blind clinical trials, the gold standard for proving a treatment works. It's a long, expensive road, but the only way to ensure safety and effectiveness. The mouse miracle gives us hope, but hope isn't a strategy. The real work is in patient, rigorous science. With curiosity and evidence as our guides, we continue exploring the mysteries of the mind.